Hello, and welcome back to Physics 41, University Physics. So let's first review uh, some of the concepts that we have discussed so far in this chapter. So, so far we have discussed the field of a moving charge. So it's given by this equation here. And basically, determine the direction, you can just use right-hand rule. The direction of the velocity is your thumb, then the direction of your the curl of your fingers are the direction of the magnetic field. The magnetic field actually curls around the path of the moving charge. But again, the direction of the curl will be reversed the event that your charge is negative. So for this lesson, we will now go on to the magnetic field of a stream of moving charges, such a way that they now create what we call current. Since current only flows on conductors, so we will try to find the magnetic field of current carrying conductors. So similarly, in the same manner, the direction of the magnetic field in a current carrying conductors obeys the right hand rule. So in this case, we don't need to reverse any directions, unlike in the moving charge. When you have a negative charge, you need to reverse. But since we will only be talking about conventional current, wherein it is assumed to be the flow of positive charges, uh, uh, again, the actual, the actual charges that flows in a conductor are electrons, positive charge. But anyway, since electricians and electrical engineers have made the convention that the current is a flow of positive charges, then we'll just go with it. Anyway, they just reverse the direction. It's just there's no mathematically there's nothing wrong. But again, physically, in a current carrying conductor or in a current carrying wire, actual charges that are moving are electrons. So here we have a conventional current moving in this direction. Then the magnetic field will be curling around the wire. It will be curling around your conductor. And the magnetic field is given by this equation. So this equation is derived from the equation for the magnetic field of a single moving charge. But if you now have a stream of moving charges, then you need to integrate all of those moving charges, hence the integral here. So this equation or law or equation is called the law of Biot-Savart. Biot and Savart. So they are the ones who derived this expression, law of Biot-Savart. Of course, the magnitude of this is just given by this equation. In this lesson, we will only consider magnetic field at points near a long straight current carrying conductor. In that case, this equation will reduce to this equation. If you're only trying to find the magnetic field near a very long straight current carrying conductor, then the magnetic field is just a law of Biot-Savart just simplifies to this equation. So in a three-dimensional view, this is the direction of the magnetic field. You will notice that above the wire, magnetic field is out of this plane and it will go inside this, actually curling around the magnetic field. And as opposed to the magnetic field of a moving charge, the magnetic field of a long straight current carrying conductor only depends on 1 over r, as opposed to the moving charge, which is 1 over r squared. If you are trying to find the magnetic field near a long straight current conductor, then the magnetic field is inversely proportional to r, not r squared. But still, as you go away from the wire, the magnetic field will not as fast as the magnetic field of a moving. 1 over r squared, just 1 over r. Okay. Uh, so, if you try to place a compass around the wire, you will notice that the direction of the compass needle will change actually. It will conform to the direction of the magnetic field. In this case, if this is your current moving out of the page actually, then the magnetic field will curl around the wire in a counterclockwise motion. So if you place a compass here, the direction of the compass needle will be like this, indicating that the direction of the magnetic field at this point is southwest. If you place the compass here, then the direction of the compass needle will be pointing east, uh, implying that the magnetic field at this point is also pointing east. Here, if you place the magnetic field at this point, it will point north, implying that the magnetic field at this point will point north. So it's actually forming a circle, or it's curling around your wire. Now, this take note that in your previous lessons in current, electricity, uh, current and EMF, resistance and EMF, electromotive force, the reason why the charges are moving is because of the non-electrostatic field produced by your potential difference, your electromotive force, EMF. The EMF is actually pushing the charges along the non-electrostatic field. So when I say this electric field here, not the electric field of this charge here. So it's due to the EMF, or the voltage, or the battery of your battery, or the source of EMF of your wire, for that matter. So you will notice here the duality of the electric field and the magnetic field. So if there's an electric field along the wire, there's a magnetic field curling around it. So in totality, we call the combination of electric and magnetic field as an electromagnetic field. And they are always perpendicular to each other. In other words, the magnetic field curls around the electric field, and in the same manner, electric field will curl around a magnetic field. For instance, if you have a conductor again, there's now a magnetic field inside the conductor, you will expect that there will be an electric field curling around your wire with magnetic field. So let's test your understanding. Okay, here we have a simple circuit, battery connected to a wire, a resistance in the wire. Place a compass needle on top of the wire. Initially, the compass needle is pointing north. So that's actually, it's just actually pointing the direction of the magnetic field of the earth at this point, which is pointing north. Now, what orientation, or which orientation of the battery? This orientation, where the positive terminal is upper side, or this orientation where the positive terminal is in the lower side, will create, or will make the compass needle deflect counterclockwise in this manner. Think about it for a second. Okay, 1 second is up. So the initial magnetic field is in this direction, and the final magnetic field is in this direction. So what should be the magnetic field of this wire, or due to the current carrying conductor, such that the final magnetic field will be this one, given this initial magnetic field? So vector addition, right? You add the initial magnetic field of the earth plus the magnetic field of the wire. So in this case, the magnetic field should be in this direction, right? Head to tail method of vectors. Initial, the magnetic field of the earth plus the magnetic field of the wire, and that will result in the final magnetic field here. Now, if you will notice here, the magnetic field of the wire on top of the wire should be pointing west. In that case, according to the right-hand rule, if it's pointing west in that direction, then the direction of the current should be downward at this point, or at this segment of the wire. which means that the orientation should be, or in this case, the current is flowing along the circuit in a clockwise motion. And the orientation that will give this clockwise flow of current is orientation as conventional current I goes out from the positive terminal of the battery, goes inside the negative terminal of the battery, and then goes again clockwise. This, okay. Even though we're just discussing magnetic field in this, let's now have a segue. Go back to the force. In the previous chapter, I've discussed about the force exerted on a current carrying conductor. But since a current carrying conductor, for example, a current carrying wire, also has a magnetic field, generates its own magnetic field, then it can actually exert a force on other current carrying wires. So we will try to find what's the force between parallel conductors. Because this is fairly common, right? If you have a wire, you strip, say, an electrical wire, you will notice that an electrical wire actually composed of fibers of wire, right? Fibers of copper wires. And each of these wires carry current, are current carrying conductors. And it just so happened that they carry current in the same direction. So this wire here will carry current in that direction, that direction, that direction, and so on. So what's now the force between these parallel current carrying conductors? So let's try to analyze this. So we'll just analyze two strands of wire. So this is wire number 1, wire number 2, assuming they carry different currents. So the magnetic field due to this lower wire will be this direction, using by virtue of right hand rule. And for the at the location of the upper wire, the direction of magnetic field due to this lower wire here is this direction. So since the current here is flowing in that direction, I cross B, then there will be a force towards the source of your magnetic field. So essentially, this wire will exert a force on the parallel wire towards it. The force is actually attractive. And in a similar manner, since this upper wire also is a source of magnetic field, this will also create or exert a force on the wire, on the lower wire. And the force is also attractive. So the force between these parallel wires are actually attractive. So when current is now flowing through these wires will stick to each other like magnets, essentially. So they will exert an attractive force between them. So in another analogy, that's it. That's the another analogy. So the force is attractive if the current is in the same direction. Fairly common in electrical wires. So the force per unit length between parallel conductors is given by this. So it's mu naught I1, the current in the first wire, I2, the current in the second wire, 2 pi. R is the distance between the two wires. And it's actually the unit called ampere is actually based on the measurement of the force between two parallel conductors. So 1 ampere is actually defined as that unvarying current that is present in each of two parallel conductors of infinite length and 1 meter apart in empty space causes each conductor to experience a force of exactly 2 times 10 to the negative 7 newtons per meter of length. That one, that's the definition essentially of 1 ampere. So let's now go on to some examples. So first example is the magnetic field of two parallel wires. So you have two long straight parallel wires are 10 centimeter apart carry equal current of 4 amperes. And the direction here is in out of the page towards you. The wire is actually perpendicular to this plane here. The wire is actually directed towards you. Hence, the direction of the current is also towards you. So you are asked to find the magnitude of the magnetic field at 3 points. For letter A, you are asked to find the magnetic field at point P1, which is midway between the wires. Point P1, in the middle between the two wires. For letter B, point P2, 25 centimeter to the right of P1. So since 10 centimeter, so meaning this is 5 centimeter and 25 centimeter to the right of P1. So meaning you measure again another 20 centimeter, and this is the location of your P2. 25 centimeter to the left of to the right of P1, and in this case it's 20 centimeter to this wire here, and it's 30 centimeter to this first wire here. And then P3, point P3 is 20 centimeter directly above P1. So directly above P1, this is your P3 here, and 20 centimeters directly above. These are our problems, or our points for our problem, where we need to find the magnetic field. Point P1 is here, point P2 is here, point P3. Okay. So let's first start with P1. Before we start, let's name our wires first so that we will not be confused. I will call this, I'm not going to call this A and 1 and 2 because we have 1 and 2 subscripts. I'm not going to call them A and B because B is also our symbol for magnetic field. We're confused with B. So instead, I'm going to call this wire C, and this is wire D. Wire C and wire D. Okay, I think that's good. Wire C and wire D. Okay, so the magnetic field at P1 will be due to wire C and wire D. So, what's the magnetic field due to wire C at point P1? So, notice the direction of the current is out of the plane or out of the page, meaning direction of the magnetic field around this wire is counterclockwise. So, counterclockwise. So, at this point, due to wire C, the magnetic field will be upwards, directed upwards. Oh, what happened? This is the magnetic field due to wire C at point 1, BC1. It's upward. And due to wire number 2, since wire D, wire D, it's also counterclockwise, but at point P1, so counterclockwise na, but at point P1, direction of magnetic field due to wire D will be downwards. BD1. That one. So you try to solve. We know now the magnitudes. You try to solve the. We know now the directions. We now try to solve the magnitude. So, for instance, if we will define the upper direction as our positive y-axis, lower direction as our negative y-axis, then BC1 is essentially just magnitude, say BC, or BC1, and its direction is j hat, positive j hat. And for this magnetic field here, BD1, its magnitude is just BD1, direction is negative J hat. And then we add these two vectors. So let's now try to find BC1 and BD1. So to solve this, we just need uh, the formula. That's the very simple formula. BC1 will just be mu naught I. They have the same current, so I over 2 pi R, say RC1. RC1 is the distance from C, our wire C, to point P1. That's the distance RC1. And similarly for BD1, just mu naught I over 2 pi R D1, the distance from wire D to point 1. In this case, they actually have the same distance because this is midway. So 5 centimeters. And this will make our two magnetic fields equal. Because they have the same current, they have the same distance. So take note, the magnetic field only depends on current and the distance, R. Take note, I will just like to emphasize this is perpendicular distance, shortest distance from the point to a wire. So essentially they're the same. They have the same magnitude, but they have opposite direction, meaning if you add this two, you will get 0. So I will just leave these details to you, but essentially these are the same. So meaning if you want now to solve for the magnetic field at point 1, just BC1 plus BD1, but these two have the same magnitude but opposite direction. So they will cancel each other out and you will get a value of 0. So for letter A, the answer is A. So how about point P2? So point P2, we will use the same analogy. So at point P2, due to wire C, counterclockwise ang direction sa magnetic field. So meaning, counterclockwise at point P2, due to wire C, the direction of the magnetic field will be upward. Is B C2. And for the wire D, it's also clockwise again. So at this point here, also upward. We have the same direction, BD2. So in a similar manner, the magnetic field at point 2, just the magnetic field due to wire C at point 2, the magnetic field due to wire D at point 2. So you just add the two. So you already know their directions. The direction is positive along the positive y-axis, so that's J hat. So solve for the magnitudes using the formula. So for B C2, just mu naught I, they have the same current, over 2 pi RC2. And for BD2, just mu naught I over 2 pi RD2. RC2, the distance from wire C to point P2, and that is 30 centimeters. RD2 is the distance from wire D, point P2, and that is 20 centimeters. So you will expect that the magnetic field due to D is stronger because it's closer to the point, while the magnetic field of wire C will be weaker since it's farther from the point. So BD2 will be much greater than BC2. So to more accurately represent our vectors, I'm gonna trim the height of BC2 to that one. BD2 in this case is much greater than BC. So you substitute the values. RC2 I is 4 amperes. RC2 is 30 centimeters. RD2 is 20 centimeters. And then you add the two vectors. So in this case, you just add the two magnitudes because they have the same direction. No need to subtract. And in this case, you will get, please recheck this now, because I haven't rechecked all of my, as a rule, you need to recheck all of my calculations. I don't use calculators. I don't have a calculator. I don't use calculator. Okay, so in this case, the magnetic field at point 2, the total magnetic field at point 2 will just be this one, BC2 plus B2, and you will get a value of, please recheck this, 6.67 times 10 to the negative 6 Tesla, and the direction is j hat. Of course, it's j hat because the two vectors are along j hat. You do the same again for point 3. You do the same for point 3. So you find the magnetic field here at point 3 due to C and D. So at this point here, the magnetic field due to wire C counterclockwise, so it will be somewhere northwest, BC3. And due to wire D, still counterclockwise, so at this point here, the circle will be pointing, line tangent to the circle will be pointing southwest. BD3. So in this case, it is safe to assume that they will have the same magnitude because they are both equidistant to the point 3. So similar to here, the length of our vectors, the magnitude of our vectors will be. Take note that these two vectors have now two components. So assuming our direction, this is the positive x-axis, so it will be this direction. To the right will be positive I hat, to the left will be negative j hat. Upward will be positive I hat, negative I hat. Upwards is positive j hat, downwards is negative j hat. So you now need to find the components of these two vectors here, BC3 and BD3. But since they have the same length, you will notice that their y components will cancel each other out. So for instance, BC3 will have a positive y component and negative x component. On the other hand, BD3 will have a negative y component, also a negative x component, because BD3 is in quadrant number 3. All of its components are negative. But these two components here, these two y components, will actually cancel each other out. So all you need to solve for is actually the x components. Again, you can do those shortcuts as long as you justify them. You write your justification. So that you have a justification to no longer solve for the y components of each vectors. So in order to find their x components, we need to find the directions of these two vectors. The directions of these two vectors is actually related to this triangle here. So specifically this angle here, this angle theta. So if you solve this triangle, 5 centimeter one side, 20 centimeter on the other side, this is a right triangle, then you will solve this angle theta, you will get a value of 75.96 degrees. And you will use this direction to solve for the x component. You use cosine. So in this case, b cosine theta. You multiply the magnitudes by cosine of this. For instance, BC3x, for instance, will be the magnitude BC3 cosine theta. And similarly, BD3X will be, actually they will have the same direction. BD3 cosine. By the way, when you use this direction, this example, this is actually not the uh, standard direction. The actual direction, for instance, this is our BC3. The theta is actually just this angle here. If you want to get formal, the angle or the direction of BC3 vector is actually measured from the positive x-axis counterclockwise. So you need to add 90 degrees to this if you want to get formal with the solution. Similarly, for BD3, the theta actually is just this direction here. That's your theta. So you need to add 180 degrees if you want to find the standard angle direction of BD. But using cosine, this value will suffice for our for this problem. You just add the negative signs. So you can use these angles, but you add a negative sign in finding your final vector. So essentially, you just add the negative sign when doing the final solution. Anyway, you need to add these to the negative values of this because they're both are negative x components. So you do that. Again, you already know how to solve the magnitudes. U naught I over 2 pi r. By the way, r is the distance here. Distance from the wire to the point. In this case, the right angle, you use Pythagorean theorem. So in this case, the magnetic field at point 3 will be 1.88 times 10 to the negative 6 Tesla, and the direction is negative I hat. This is the magnetic field at point 3. Direction is negative I hat, or towards the negative x axis. Okay. What is now? If you try to show, to look at the pattern, I'm just gonna erase this because this our slide or our board is now very messy. What is now the pattern that you see? Point P1, magnetic field here is 0. This is point P3. The magnetic field there is actually to the right, to the left. And at point P2, somewhere around here, magnetic field is actually upward. So what can you predict of the pattern? So actually on this side, to the left of wire D, the magnetic field is actually upwards. To the right of to the left of wire C, the magnetic field will be downwards. So you will expect a pattern something like so. That's the magnetic field pattern of two parallel wires with the same current flowing through them, same current and direction. So there will be zero magnetic field exactly at the middle. In the event that you have two parallel wires with opposite directions of the current, then the magnetic field looks like this. So the magnetic field in the previous example is the magnetic field pattern of attraction between two wires. This is the magnetic field of repulsion between two wires. Take note, the force is attractive if the current is the same in two parallel wires. So the pattern will be like this. So instead of having 0 at the center, we'll have a maximum value center, or at the midway between the two wires, no longer 0. And it's symmetric. You'll notice it's symmetric. The magnetic field pattern is symmetric, unlike in the previous example where it's still has the counterclockwise pattern. Okay, so let's move on to another example. Actually, this is the last example for the lesson. Essentially for the chapter. No, still in lesson. So, magnetic field of intersecting wires. You have 4 very long current carrying wires in the same plane, lie on the same plane. They intersect to form a square 40 centimeter on each side. This is now our square. The length of each side of the square is 40 centimeters. Find the magnitude and direction of the current I. So there's an unknown current in this configuration. This wire has a current of 10 amperes flowing upward. This wire here has a current of 8 amperes flowing to the right. Similarly, this other wire here also carries a current to the right, but has a magnitude of 20 amperes. So there's a wire here, and a known current I. Don't know the magnitude of the current, we don't know the direction of the current. And current is a vector. So find the magnitude and direction of the current I so that the magnetic field at the center of the square is 0. So at the center, at this point here, the magnetic field should be 0. Okay. Seems pretty easy. You just need to add the contribution, the magnetic field contribution of 4 wires. So I will name this as wire number 1, wire number 2, wire number 3, and the wire with the unknown current is wire number 4. So you just need to I'm just gonna set up the solution for this case now. So the magnetic field at the center will just be due to the magnetic field of the 4 wires, B1, B2, B3 plus B4, and this is all equal to 0 because add the contribution of the 4 magnetic fields at the center should be 0. That's the initial condition. So the unknown in this case is B4. So essentially, we need to solve for the magnetic field at due to wire number 4, and it's just negative. You transpose all of this to the other side of the equation, you get negative B1, B2, negative B3. Okay. So to easily solve this problem, we will define our directions of our vectors, our axis, for instance. The vector that is vectors that are out of the plane are in the k hat, the positive z-axis, and the vectors that are into the plane have a direction of negative k hat, or towards the negative z-axis. Now, start with wire number 1. Wire number 1 has a current moving to the right, meaning, according to the right-hand rule, the direction of current is in this direction, then the current will actually curl around the wire in this manner. So at this side of wire number 1, the current will actually be going into. It will curl around, so it will go into the feed. So the direction of into is negative k hat. So essentially, B1 here will just be, have a magnitude of B1. You can calculate that. It's at mu naught I1 over 2 pi R1. In this case, the distances, the perpendicular distances of each wire to the center will just be distance here, which is half of 40 centimeters, so 20 centimeters. So the R's are all the same. It's 20 centimeters. So the direction will be negative k hat. For B2, so For B2, same curl, but in this case, on the upper side of wire number 2, the current will actually be out of the page, then into other page in this side here. It will curl around manner. So just B2 positive K hat, it's out of the page. And then for B3, going up, so the direction, so this side here of wire number 3, out of the page, and opposite side, it's into the page, so negative K hat. We have minus B3 is B3 and negative K hat. Okay, so you can now solve for B4. So again, B1 is just mu naught I1 over 2 pi R1. B2 is mu naught I2 over 2 pi R2. And the R1, R2, and R3 here are all the same. R1, R2, R3, R4. Distances from each of the wire to the point. 20 centimeters. So this is your starting point. So I need you to continue this so that you can find the value of your magnetic field. So you can now solve for the magnetic field B4. You now have solved B4, then you equate this mu naught to mu naught I. Just take its magnitude. Actually, from the direction of B4, you can now deduce also the direction of the current. So if the direction of B4 is positive K hat, out of the page, meaning the current is upwards. Or if the direction of B4 is into the page, meaning the current is downwards. So you can now deduce the direction of the current in wire number 4, provided you know the direction of B4. So mu naught I over 2 pi R. So to solve for the magnitude of the current, knowing B4, manipulate this equation to solve for I. Then you can get your final. So I guess the final answer is 1 ampere downward. So final answer is 1 ampere downward. So the current is flowing downward. The value of the current is 1 ampere. But again, try to recheck. Maybe I made a mistake in my calculation. But this is the solution. Our solution is correct. Okay. Okay, so that's the last example for this. So that's the end of the second lesson for this chapter. So we are just finding the magnetic field of a straight current carrying conductor. Now, in a similar manner with what we have in the previous chapter, what if our conductor now form a loop such that they create a current carrying loop or a current loop? So what is now the magnetic field of that current carrying conductor? We'll discuss that in the last lesson for this. I will see you again in the next